Welcome to Study Loop.
So for the given monatomic gas, we have to sketch the pressure volume diagram for the given cyclic process ABC. Now, this process can be observed as a three-component process. So the first component would be from A to B, the second component would be from B to C, and the third component would be from C to A backwards. This is a cyclic process, and the initial and final points of the process are the same. As given in the problem, we know that the heat flow overall for this process is negative. It's minus 100 joules. And therefore, the change in temperature will occur as well. So for the first part of the first part of the cyclic process will be from the point A to the point B, and this can be drawn as a line parallel to the horizontal axis, which is the volume axis. So here's the point A, here's the point B, and in this case the pressure will be constant, so only the volume will change. Next, for the second part of the process, it will be from the point B to the point C. And in this case, the volume will not change, but as given in the problem, only the pressure will increase. It will be compressed. So this will be a straight vertical line. And this is the point C. Next, from the point C to the point A, both pressure and volume will decrease simultaneously. This is where the heat exchange will happen as well, and the change in temperature also. So it will look something like this. This is a slightly curved line from the C to the A. Therefore, this is how the pressure volume diagram will look like. And one thing to note here is that since the starting and the ending point are the same point, the internal energy change will be equal to 0. So it is always equal to 0 for the cyclic processes. This is an important thing to notice. But there will be a change in temperature. And this change in temperature will be useful for the part B of the problem. So for the part A, we have solved the part A. The part A was to draw the PV diagram, and the corresponding PV diagram is drawn right here. Now for the part B of the process, for the part B, we need to find the total work done. From the total work done, we need to find the work done from C to A. This is the slightly curved line on the PV diagram. So we know that the total work is equal to addition of every work component, of the component that is corresponding to each process component. BC and WCA. So to derive the part of the final component process, it will be WCA equals WT minus WAB plus WBC. From the PV diagram, we can see that for the BC part of the process, the BC line will be on the constant volume. So if there is no volume change, there is no work done. Therefore, this will be 0. Only this part of the work will contribute. And in this case, for the WAB, now we will use the ideal gas equation. So because the work from A to B is under constant pressure, but the volume changes, so it will be delta V. Now, from the ideal gas equation, we know that P delta V can be related to nR delta T, or the change in temperature. So we can substitute that AB work is actually number of moles times gas constant times the change in temperature B minus TA. Substituting this back into the equation for the work CA, we obtain that work CA, and we can immediately substitute minus 800 joules. This is the total work done, and then also negative nR TB minus TA. Then we can substitute other of the known values, which is the number of moles. This is 2 moles times 8.314 joules per mole kelvins times the difference in temperature. Substituting all of these values into a calculator and evaluating the final number, we obtain that the value of the work done from C to A is equal to minus 2,463 joules. And this is the final answer for the part B of this problem. So we see that the work done, and let's return for a short time to the PV diagram, we can see that the work done in this case, for this from C to A, is negative. And the temperature changes as well in this case, not only pressure and volume at the same time. So this is a cyclic process. We know the overall work for the process, but the process in this part from C to A is very negative. It is 2,463 joules negative energy. So the energy is being liberated from the system, meaning that the system accumulated some energy during this part of the process here, since there is no work done in this part of the process. But still, the overall energy is also negative 800 joules, as given in the problem. This completes the problem, and I hope you find this helpful, and I hope to see you in another lesson.